So today we will continue the three-phase transformer topics. The objectives of today's class is to recognize the phase shift between primary and secondary of different connections of three-phase transformer, analyze the three-phase bank transformer, recognize the equivalent turns ratio for different transformer connections, and analyze the open delta transformer performance. We agreed from the last class that three-phase transformer can be constructed by using two different ways, either connecting three single-phase transformers together or creating a complete core for the three phases. And we agreed together that if we use three single phases, we have, when we connect this transformer as a star or delta connection for both primary or secondary, we have to consider the flux direction and dot coil rule when connecting the three phases together in order to establish the flux in the right way. Okay, and we agree that if we have a problem with one phase, we can remove one of the phases or one of the transformers in order to make maintenance for this transformer. And this is going to be discussed in this class in what's called open delta or V connection. We agreed also together that if there is a different connection between primary and secondary, so and we discussed we have four different connections: star or Y delta, and delta Y, and Y and delta delta connections. So we have four different connections. If the primary and secondary are different, which means Y delta or delta Y, this is going to make a phase shift between the voltages or line-to-line voltages of the two sides. For instance, if we have Y delta transformer like that, and here we can see that the line-to-line voltage here, which is VAC for instance, or let's VAB, between these two terminals, VAB, and VAN is just this volt. So the relation between VAN and VAB can be recognized here from the phasor diagram. As you can see, VA, if we assume VA in this direction, so this is VB and this is VC, 120 degree phase shift between all of the three phases. In order to get VAB, we need to calculate VA minus VB. Is there a question, Shabab?
Excuse me, doctor, can you repeat?
Okay, again, we have now Y delta connection. The relation between phases of Y connection, as you can see, VAN here, we assume this is the reference now, and VB is shifted by 120, and VC is minus 120. So, what is the relation between VAN and VAB for the same side here for the star connection or Y connection? We can find that VAB equals VA minus VB. So you have here VAN, this is VBN, and this will be minus VBN. So the resultant vector of these two vectors, the summation of these two vectors, will be VAB, which is the line-to-line of Y connected. This is what we have described already previously in three-phase circuits. So, as you can see, there is a phase shift between line-to-line voltage and line-to-neutral or phase. This is the nature of star connection. Right. Regarding the delta connection, we agreed also last class that the flux or the EMF will be generated on the secondary side will be related to the phase value. So the value of V here will be transferred to V on the other side, but with considering the turns ratio. So if it is A here, if it is value of V here, and the other side will be V over A, which A is the turns ratio of transformer. So we expect to have VAN of Y connection and VA of delta connection we expect these vectors to be in phase. So the delta connection here, this is the phasor diagram which represents the voltages of the delta connection. VA or VAB will be in the same direction like VAN. In this case, you will find that the phase shift between VAB of delta connection and VAB of star connection, the phase shift is 30 degrees now. So if you have different connection between primary and secondary, different connection means Y delta or delta Y. So you will have all of time a phase shift between the two coupling voltages by 30 degrees. And this is very important and used a lot in many applications. And we described one of the applications like the interconnection between Egypt and Saudi Arabia, interconnection between any country, okay, any two countries, using rectifier converter stations, okay, which is the type of 12 pulse rectifier. 12 pulse rectifier needs two sets of three phases with a phase shift of 30 degrees. So we use transformer. The primary winding is star connected, and second winding is divided in two halves. Each half is connected in different way. One half is connected as a star, and the other half is connected as delta. So this is going to make different phase shift for the secondary voltages, for the two halves of the secondary voltage. Okay, شباب? So this is one of the applications used or depend on the phase shift between the delta and star connection. Right. Now, in order to analyze the performance of the three-phase transformer, it's not easy to solve circuits with the exact equivalent circuit of the transformer of the single phase one. It's not easy to make it the same as three phases. If you remember, for the exact equivalent circuit, we may need 2 or 3 loops in order to solve any problem, okay, for the exact one. However, for the approximation, we try to make some approximation in approximately equivalent circuit 1 and 2 in order to simplify the method or the circuit, in order to simplify the mathematical analysis, okay, to solve or analyze the problem. For three-phase, it will be more complex. So we need also to simplify to another circuit in order to simply make circuit analysis for the transformer, for the three-phase one. So simply, the method is called single-phase equivalent circuit. We have to convert the three-phase into single phase, and this needs some requirements. If the load, if the transformer is connected as a star or delta, you need to, if it is star, it's okay, you can convert to single phase directly, because we can consider each phase of the star connection as single phase, and we can consider only one of the phases and solve the problem. However, if you have delta connection on any side, primary or secondary or load or whatever, you need to convert this to star connection, okay? And we already studied before how to convert delta to star. And simply, if you have load impedance of ZL, 3 balanced load like that, and you need to get the equivalent star connection, so the value of impedance here will be Z load divided 3. Take care. This conversion is virtual conversion. The impedance value is still the same. However, virtually, we convert the connection from delta to star in order to analyze. However, the actual connection is still delta. Okay. Also, the same for the transformer itself. We need to convert this delta into star. Right. How we can do that? If we have the transformer like that, this is now the star connection of transformer of the primary. So it's ready now to be analyzed or converted to single phase easily. The current which is moving from the line is the same as the current moving in phase. So this is the final equivalent circuit we need. So as you can see, this is I is the same as the I here in the star. Now, for the voltage here on one phase, if you have V as line-to-line voltage, so the voltage applied to the N1 here, N1 coil, will be V over square root of 3. So this is now the applied voltage to the single phase equivalent circuit. And what about the number of turns? If it is Y connection, so the number of turns will be the same. It's N1. Regarding delta connection of the secondary here, we agreed together that the amount of volt of the phase will be transferred to the other side with respecting the turns ratio. So the amount of volt in phase here is V divided or over square root of 3. So it will move to the other side and dividing by the turns ratio. So the relation now will be the voltage here is V over square root of 3 multiplied by turns ratio. This is the voltage of the phase. And it will be the same also for the line because this is delta connection. So now if you make a black box here, just adding box here, and you know now the line-to-line voltage, and you need to convert this black box into star connection. For sure, the line-to-line voltage has to be the same. We don't change anything in the circuit. We just virtually will convert the delta into star. So the voltage here will be the same, and virtually this connection will be converted to star, which means the phase volt of the virtual star equals V line over square root of 3. So this is going to make the voltage here equals V over 3A. Okay, is it clear, يا شباب?
Yes, doctor, it's clear for me.
Okay, good. Is there any question regarding this part? Shall I repeat it? Okay, very good. Right. For the current, let's return back again to the current in order to recognize again the transformation. Here is the current of Y. So we expect in the phase here to have a current multiplied by the turns ratio. Right. This is for the delta connection, and you know for delta connection, the line current equals the phase current multiplied by square root of 3. So the actual line current will be square root of 3 multiplied by AI. So again, consider this as a black box now, and we need to convert to star connection. So the same values of line to line will be the same here and here. So the same line to line volt, the same line current, and to convert here this to star. In this case, the phase winding or the virtual phase winding of the star equivalent circuit, the current will be the same of the line one. Okay, Shabab, is it clear now? So now we can consider one of the phases here to convert it to single phase. For that, the voltage will be V over 3A, as you can see, and the current will be square root of 3 multiplied by IA. So this is now the equivalent circuit of the star delta connection, okay, as single line, star, and equivalent star. Okay, Shabab? So this is now the single phase equivalent circuit. Take care that the turns ratio now will be N over N2 over square root of 3, because you consider already converting from delta to star, okay? And this is going to make turns ratio by square root of 3 like that. تفضل عن سؤال.
Here he didn't pay attention to the angle.
Sorry?
He didn't pay attention to the angle.
Here, yes, you are right. We didn't pay attention to angle. However, we should consider during solving problems. Now you just now considering only the absolute values of magnitudes of voltage and the current. And we can see how we can solve problems using that. Okay? Right. Any questions, Shabab? Okay, let's have a numerical example in order to understand more the operation and transformation between three-phase equivalent to single-phase equivalent circuits. The example here says 3 single-phase 50 kVA, 2300 over 230 volts. So we have 3 single-phase transformers, okay, and this is the S rated for one phase, and the V primary is 2300 and the secondary is 230, and the frequency is 60 Hz. If we are going to connect these 3 single-phase transformers to a 3-phase transformer, so 3 single-phase transformers are connected to form a 3-phase 4000 over 230 volt. So the required now is to obtain this turns ratio or these voltage levels from the 3-phase transformer. How? We can see how we can get this required voltage. So the required is to make 3-phase transformer bank of 4000 over 230 volt. The equivalent impedance of each transformer, these data are for the single phase one. The equivalent impedance for each transformer refer to low voltage side. Low voltage, it means to the 230, which is the secondary now. Okay. So the value of the impedance, the equivalent impedance, is 0.012 plus J 0.016. So this is now the Z equivalent refer to secondary or low voltage side. The 3-phase transformer supplies a 3-phase load of 120 kVA, 230 volt, 0.85 power factor lagging. What is needed here? First, draw a schematic diagram for or showing the transformer connection. Right. Let's start firstly from the required voltages. Now, you need the secondary of the single phase one to be the same like the secondary of the line-to-line voltage. What is the connection that the phase and line voltages are equal? Which connection we have this property?
Delta.
Delta connection.
Delta.
Right. So we should consider the secondary connection now as delta in order to obtain or make the similar to the line volt. Take care all of time the values of turns ratios for the 3-phase transformer all of time is the line-to-line volt. So now the phase 230 should be aligned to 30, so this connection should be delta now. So the secondary is delta connection. And here we have our load. Whatever the connection of the load, we don't care, it's not mentioned in the problem. However, we know only the apparent power needed and power factor. And this is the line-to-line voltage needed here. And this is the secondary connection of the 3 single-phase transformers. Regarding the primary, now the single phase can support 2300 volt. The required coupling volt or line-to-line volt of the 3-phase equivalent is 4000. If you see the relation between 4000 and 2300, you will find the relation is square root of 3. So 2300 multiplied by square root of 3, this gives you the 4000, approximately the 4000. Okay, Shabab? So in order to achieve line-to-line of 4000, it means you need to connect the primary as a star connection or Y connection. Why? because in Y connection, the line to line equals square root of 3 multiplied by the phase 1. So we have to connect the primary as star connection like that. In this case, if you supplied 4,000 from this side, assuming ideal transformer to test the turns ratio, if you supply the 4,000 here, only 2,300 will be applied here, and according to the turns ratio of the single phase, which was 10, so 230 volt will be appear on the phase here, which will be the same as line. So in this case, we could achieve the same required voltage levels of the transformer. So the right connection now should be Y delta connection. Is there any question, Shabab, regarding this part? Is it clear? Okay, good. Number B, determine the transformer winding currents. Now we have many currents. We have primary currents. We have two secondary currents because it's delta, so we have phase and line currents. So we need to calculate all of these. In order to calculate currents, we have the voltage values. So we need first to use the impedance in order to get current. Right. For the impedance, now the impedance is given referred to low side. Low side, which is the secondary of the transformer. So in terms of power, we can get it firstly in terms of power, Shabab. No need for the impedance now. And we are going to calculate from the load side. We have the load side, which is 120 kVA, and you know the line-to-line voltage here. So what should be the value of IS, Shabab?
The balance power over the voltage, line voltage.
Can you express the relation? What is the relation exactly?
S equal IV.
S equal IV. This is right. So we have S equal 120 and V equal 230. So IS equal 120 over 230, but over square root of 3 because this is now three phase. Is it right?
Oh, okay.
Right. So the relation is S equal square root of 3 multiplied by V line, I line. So for now, we can simply get IS as the 120 kVA divide square root of 3 multiplied by V line. So this is now the value of line current without considering any angles now. It's just needed the value of currents. But if the line current is calculated, what will be the value of phase now, Shabab?
The line current divided by root 3.
Exactly right. So I2 is the value of line current over square root of 3, which is here 173 ampere. Right. This is the current of the phase. In order to get the other phase, we can now use the turns ratio. So we can say I1 divide I2 equals 1 divide A. And A here equals A, Shabab, huh? Which A we should consider now? Now we're converting phase with phase.
The single phase.
The single phase one. This is right. This is completely right. Can you, is there any problem, Shabab, regarding this part? Why we are going to use the 10 turns ratio of the other one? Now we have the current of this phase, okay? And the phase is coupled with the phase. So we can use the phase to phase turns ratio, which is this one. So we can say I1 over I2 equals 1 over 10. So simply we can say I1 equal I2 over 10. So this is now the value of the primary current for the star connection, which is the same as the line current. Also, it's required to determine the primary voltage. Now, in order to get the voltage, so we should find the single phase equivalent circuit and start using circuit analysis to obtain the input voltage. So the impedance we have now in the problem is referred to secondary side. We need to convert to primary side and solve all of the problem related to or referred to primary side, so we can get Z equivalent 1 referred to primary, so we have to multiply by terms ratio square. طب شباب يعني should we multiply or divide؟ يا شباب يعني in order to not be confused, يعني now we are moving impedance from secondary to primary, is it right?
Yes.
Okay, so you are moving from side 2 to side 1, so you should respect the side you are going to.
Yes.
Again, you should respect the side you are going to. You are going to side 1, so start by N1, which means if you are going to move impedance or volt from side 2 to side 1, so multiply by N1 divide N2. Again, you are going to move from side 2 to side 1. Here, you are going to move from side 2 to side 1. So respect or start with the side you are going to. So you should multiply by N1 divide N2, which is A squared. Voltage and impedance, respect this ratio. Respect the place you are going to. Current is not respecting this ratio. Again, so here we are going to move from side 2 to side 1. We should multiply by N1 over N2, but the impedance ratio should be squared. So the N1 divide N2, which is the value of A, which is 10, so we should multiply by 10 squared. Okay, so this is now the value of the impedance referred to the primary side.
Doctor, why do we refer to the primary side?
Again, your question, please.
Why did we refer to the primary side?
الصوت مش واضح خالص.
Can you hear me?
انا مش الصوت مش واضح. حاول لو بتستخدم سماعات شيلها، لو مش بتستخدم استخدم سماعات لان الصوت مش واضح خالص.
كويس بستوك.
طب حد سمع السؤال يا شباب؟ يوضح لي السؤال ايه؟
اتوقع انه قال why are we referring to the primary side?
Why we referring to primary side? It's up to you. You can refer to primary side and get the voltage in primary side, or you can solve all of the problem in secondary side, and finally you should get the exact value of primary, so you can transfer the voltage only. So it's up to you. Okay, and you can solve the problem now, either all of the problem either referred to secondary, and finally you need the input voltage. Is it right? So you can transfer finally the final results only of volt. Transfer the volt from second to primary because the required volt is the primary one. Okay? Or you can transfer the impedance of transformer to primary and solve it in the primary and get the ready volt out of A in the primary side. Okay? And it's up to you. You can solve either refer to primary or refer to secondary. The same solution. So for now, we consider referring to primary side. So we have V2 prime here, which is 2300. And the impedance here, this is our impedance. And the current was calculated before. So the angle of current, how the angle of current could be obtained. And simply, if we return back again to the impedance here, sorry, here the current, you know the value of I, we need the value now of I phase, is it right? تمام يا شباب؟
Yes, yes.
So this is now the angle, this is now the current what we need, and the angle should be obtained from the power factor. What is the power factor?
0.8 lagging.
0.85. تمام. So we can consider the angle equals cosine inverse 0.85. Okay, and this will be the angle of current now. And as you can see now, we consider the volt of 2 or 2300 volt as reference. طيب يعني one may ask me now, this is the phase current. Why we consider the phase current, not the line current, as zero? Why we consider the why we consider the angle of phase current is the same as the impedance value, not the line current, because in the beginning, as you can see, we have line and phase. Okay, صح يا شباب؟ يعني all of time يا شباب we consider the phase value. Consider the phase value in order to simplify. So يعني you already consider the phase voltage. Now also we consider the same current. So we consider the phase value here. Right. So this is now the current of the secondary after referring to primary. So it's 17. Okay. And the angle is the same angle of the impedance, considering the phase of 23 as 2300 as reference. تمام يا شباب؟ So for now, we can simply calculate V1 as V2 prime plus I multiplied by the reflected impedance. So this is now the absolute value of the primary voltage. Fine. Primary voltage here, this one is considered as phasor line يا شباب. Now we consider this as a single phase circuit. Is it right?
Yes.
This is now single phase circuit. But return again back to the connection. Single phase circuit, it means for one coil. So what will be the coupling voltage? Is it the same like the phase one? Is it similar?
No.
It should be not similar, because the line to line here equals square root of 3 multiplied by phase value. For that, we should multiply this value by square root of 3 to get the primary line to line voltage. So this is now the value. This is logic. يعني طبعا it should be like that, because in the beginning of the problem we said 4000 over 230 three-phase transformer. So it should be higher than the 4000. This is logic. تمام يا شباب؟ Number D, determine the voltage regulation. طبعا voltage regulation easily, because you already obtained the value of V input or V1. Okay, you can simply apply this to the voltage regulation relation, which is V1 minus V2 prime over V2 prime. يعني طبعا you calculate it using phase. If you would like to calculate using line, it's possible also. Okay, but in this case you will use this value with the 4000. يعني the voltage regulation is ratio, so we can consider either phase or line, no problem. Okay شباب? Is there any problem شباب regarding the solution of this case? Now we understood how we can convert the circuit into a single phase transformer, and finally we should return the values to three phase again. يعني we assume single phase, we get the single phase values, we calculate the value of V1, and finally we have to return back to the three phase again to find the exact value. Okay. يعني I think the second example will take more time. We can يعني إن شاء الله solve it in the next class. Is there any question يا شباب؟
يعطيك العافية دكتور.
الله يعافيك. في حد رافع ايده؟
دكتور ماتيريال ميد تيرم لين الترانسفور